Dr. Engineering Thermodynamics, Assistant Professor. SRM Institute of Science and Technology. Unit 4, Air Standard Cycles. Otto cycle, diesel cycle, dual cycle. Indicator diagram, air standard efficiency, mean effective pressure. Brayton cycle, effect of reheat, regeneration and intercooling. Isentropic efficiency of turbine and compressor. Equivalent Carnot cycles, Stirling and Ericsson cycle, Humphrey cycle. The devices or systems used to produce a net power output are often called engines, and the thermodynamic cycles they operate on are called power cycles. The devices or systems used to produce a refrigeration effect are called refrigerators, air conditioners, or heat pumps, and the cycles they operate on are called refrigeration cycles. Refrigeration cycle. Thermodynamic cycles can also be categorized as gas cycles and vapor cycles, depending on the phase of the working fluid. In gas cycles, the working fluid remains in the gaseous phase throughout the entire cycle, whereas in vapor cycles the working fluid exists in the vapor phase during one part of the cycle and in the liquid phase during another part. Thermodynamic cycles can be categorized yet another way. Closed and open cycles. In closed cycles, the working fluid is returned to the initial state at the end of the cycle and is recirculated. In open cycles, the working fluid is renewed at the end of each cycle instead of being recirculated. In automobile engines, the combustion gases are exhausted and replaced by fresh air, fuel mixture at the end of each cycle. The engine operates on a mechanical cycle, but the working fluid does not go through a complete thermodynamic cycle. Heat engines are categorized as internal combustion and external combustion engines, depending on how the heat is supplied to the working fluid. In external combustion engines, such as steam power plants, heat is supplied to the working fluid from an external source such as a furnace, a geothermal well, a nuclear reactor, or even the sun. In internal combustion engines, such as automobile engines, this is done by burning the fuel within the system boundaries. The main differences between mechanical and thermodynamic cycles are the working substance is not recirculated. In a thermodynamic cycle, the working substance undergoes a series of processes and is always returned to its initial state. Energy conversion. Mechanical cycles convert heat input into mechanical work output. Thermodynamic cycles allow for the continuous conversion of thermal energy into other types of energy. Thermodynamic cycle. Basic power-producing devices operate on power cycles. The cycles encountered in actual devices are difficult to analyze because of the presence of complicating effects, such as friction, and the absence of sufficient time for establishment of the equilibrium conditions during the cycle. The analysis of many complex processes can be reduced to a manageable level by utilizing some idealization. A cycle that resembles the actual cycle closely but is made up totally of internally reversible processes. Such a cycle is called an ideal cycle. The ideal cycles are internally reversible, but, unlike the Carnot cycle, they are not necessarily externally reversible. That is, they may involve irreversibilities external to the system such as heat transfer through a finite temperature difference. Therefore, the thermal efficiency of an ideal cycle, in general, is less than that of a totally reversible cycle operating between the same temperature limits. The idealizations and simplifications commonly employed in the analysis of power cycles can be summarized as follows. 1. The cycle does not involve any friction. Therefore, the working fluid does not experience any pressure drop as it flows in pipes or devices such as heat exchangers. 2. All expansion and compression processes take place in a quasi-equilibrium manner. 3. The pipes connecting the various components of a system are well insulated, and heat transfer through them is negligible. Neglecting the changes in kinetic and potential energies of the working fluid is another commonly utilized simplification in the analysis of power cycles. This is a reasonable assumption since in devices that involve shaft work, Such as turbines, compressors, and pumps, the kinetic and potential energy terms are usually very small relative to the other terms in the energy equation. Fluid velocities encountered in devices such as condensers, boilers, and mixing chambers are typically low, and the fluid streams experience little change in their velocities, again making kinetic energy changes negligible. The only devices where the changes in kinetic energy are significant are the nozzles and diffusers, which are specifically designed to create large changes in velocity. The area enclosed by the process curve represents the network of the cycle. An ideal power cycle does not involve any internal irreversibilities, and so the only effect that can change the entropy of the working fluid during a process is heat transfer. On a TS diagram, a heat addition process proceeds in the direction of increasing entropy, a heat rejection process proceeds in the direction of decreasing entropy, and an isentropic, internally reversible, adiabatic, process proceeds at constant entropy. The area under the process curve on a TS diagram represents the heat transfer for that process. The area under the heat addition process on a TS diagram is a geometric measure of the total heat supplied during the cycle chain, and the area under the heat rejection process is a measure of the total heat rejected CO. The difference between these two, the area enclosed by the cyclic curve, is the net heat transfer, which is also the net work produced during the cycle. Therefore, on a TS diagram, the ratio of the area enclosed by the cyclic curve to the area under the heat addition process curve represents the thermal efficiency of the cycle. In the Rankine and Otto cycle, which is the ideal cycle for steam power plants, the working fluid flows through a series of steady flow devices such as the turbine and condenser, whereas in the Otto cycle, which is the ideal cycle for the spark ignition automobile engine, the working fluid is alternately expanded and compressed in a piston cylinder device. Therefore, equations pertaining to steady flow systems should be used in the analysis of the Rankine cycle, and equations pertaining to closed systems should be used in the analysis of the Otto cycle. In actual gas power cycles, the working fluid remains a gas throughout the entire cycle. Spark ignition engines, diesel engines, and conventional gas turbines are familiar examples of devices that operate on gas cycles. In all these engines, energy is provided by burning a fuel within the system boundaries. That is, they are internal combustion engines. Because of this combustion process, the composition of the working fluid changes from air and fuel to combustion products during the course of the cycle. However, considering that air is predominantly nitrogen that undergoes hardly any chemical reactions in the combustion chamber, the working fluid closely resembles air at all times. Even though internal combustion engines operate on a mechanical cycle, the piston returns to its starting position at the end of each revolution. The working fluid does not undergo a complete thermodynamic cycle. It is thrown out of the engine at some point in the cycle, as exhaust gases, instead of being returned to the initial state. Working on an open cycle is the characteristic of all internal combustion engines. The actual gas power cycles are rather complex. To reduce the analysis to a manageable level, we utilize the following approximations, commonly known as the air standard assumptions. 1. The working fluid is air, which continuously circulates in a closed loop and always behaves as an ideal gas. 2. All the processes that make up the cycle are internally reversible. 3. The combustion process is replaced by a heat addition process in ideal from an external source, Fig. 4. The exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. Another assumption that is often utilized to simplify the analysis even more is that air has constant specific heats whose values are determined at room temperature, 25 degrees Celsius, or 77 degrees Fahrenheit. When this assumption is utilized, the air standard assumptions are called the cold air standard assumptions. A cycle for which the air standard assumptions are applicable is frequently referred to as an air standard cycle. An nomenclature for reciprocating cylinder between two fixed positions called the top dead center, TDC, the position of the piston when it forms the smallest volume in the cylinder, and the bottom dead center, BDC, the position of the piston when it forms the largest volume in the cylinder. The distance between the TDC and the BDC is the largest distance that the piston can travel in one direction, and it is called the stroke of the engine. The diameter of the piston is called the bore. The air-fuel mixture is drawn into the cylinder through the intake valve, and the combustion products are expelled from the cylinder through the exhaust valve. The minimum volume and clearance in the cylinder when the piston is at TDC is called the clearance volume, Fig. The volume displaced by the piston as it moves between TDC and BDC is called the displacement volume. The ratio of the maximum volume formed in the cylinder to the minimum clearance volume is called the compression ratio R of the engine. The compression ratio is a volume ratio and should not be confused with the pressure ratio. The mean effective pressure, MEP, is a fictitious pressure that, if it acted on the piston during the entire power stroke, would produce the same amount of net work as that produced during the actual cycle. Used as a parameter to compare the performances of reciprocating engines of equal size. The engine with a larger value of MEP delivers more net work per cycle and thus performs better. The Otto cycle is the ideal cycle for spark ignition reciprocating engines. It is named after Nicolaus A. Otto, who built a successful four-stroke engine in 1876 in Germany using the cycle proposed by Frenchman Beau de Roches in 1862. In most spark ignition engines, the piston executes 4 complete strokes, 2 mechanical cycles, within the cylinder, and the crankshaft completes 2 revolutions for each thermodynamic cycle. These engines are called 4-stroke internal combustion engines. Otto cycle, the ideal cycle for spark ignition engines. In 2-stroke engines, all 4 functions described above are executed in just 2 strokes, the power stroke and the compression stroke. In these engines, the crankcase is sealed, and the outward motion of the piston is used to slightly pressurize the air-fuel mixture in the crankcase. 2-stroke engines. It consists of 4 internally reversible processes. 1 to 2 isentropic compression. 2 to 3 constant volume heat addition. 3 to 4 isentropic expansion. 4 to 1 constant volume heat rejection. Processes 1 to 2 and 3 to 4 are isentropic. And V2 equals V3 and V4 equals V1. Thus, substituting these equations into the thermal efficiency relation and simplifying, is the compression ratio and K is the specific heat ratio Cp/Cv. Diesel
Process
cycle
1 to 2 is
ideal
isentropic
cycle for compression ignition
3
engines.
to 4
is isentropic expansion, and 4 to 1 is constant volume heat rejection. 2 to 3, constant pressure heat addition. The combustion process in the ideal diesel cycle is approximated as a constant pressure heat addition process. The thermal efficiency of the ideal diesel cycle. Compression ratio in petrol engines 1 to 10:1, often around 8:1 or 9:1. Lower compression ratio because petrol engines use spark ignition. Higher compression can cause knocking, pre-ignition, due to the air-fuel mixture detonating prematurely. To avoid knocking and engine damage, compression ratios are kept relatively moderate. Typical range, 14:1 to 22:1, often around 16:1 to 20:1. Higher compression ratio because diesel engines use compression ignition. The air is compressed so much that its temperature rises enough to ignite the fuel when injected. Higher compression ratios improve thermal efficiency and power output. Diesel engines don't have a spark plug, so knocking isn't an issue. Higher compression ratio means better efficiency, temperature and pressure of the air-fuel mixture before combustion, which leads to more complete combustion and higher thermal efficiency, especially in diesel engines. The octane number for petrol/gasoline is a measure of a fuel's resistance to knocking in a spark ignition petrol engine. What it measures, the resistance of petrol to knocking or pinging during combustion, premature ignition. Why it matters: knocking happens when the air-fuel mixture ignites before the spark plug fires, causing inefficient combustion and engine damage. What it
Cetane
measures,
number,
the ignition quality
fuels.
of diesel fuel, specifically, how quickly the fuel ignites after injection into compressed hot air. Why it matters: a higher cetane number means the fuel ignites more readily, leading to smoother engine operation and easier starting. TS and PV diagrams for the ideal diesel cycle. TS and PV diagrams for the ideal petrol and diesel cycle. Diesel cycle ratio RC, the ideal cycle, as the ratio of the cylinder volumes after and before the combustion process. The thermal efficiency relation reduces to where R is the compression ratio. PV diagram of an ideal dual cycle. Why the ideal dual cycle is important. Real diesel or compression ignition engines don't have combustion that happens purely at constant volume, Otto cycle, or purely at constant pressure, diesel cycle. Instead, combustion is a mix of both. Some of the heat release occurs quickly, closer to constant volume, and some occurs as the piston moves, closer to constant pressure. The dual cycle captures this mixed behavior better than the Otto or diesel cycles alone. Bridge between Otto and diesel cycles, the dual cycle effectively combines features of both Otto and diesel cycles, providing a continuum to analyze how real engines behave. It's a more flexible model that can adjust parameters to mimic different combustion characteristics. Insight into engine design and performance. Studying the dual cycle helps engineers understand how changes in combustion timing and heat release impact efficiency, power, and emissions, even if the cycle itself isn't real exactly. It's a useful tool for optimization. Educational purpose. It deepens your understanding of thermodynamics and internal combustion by showing how heat addition mode affects engine behavior. This knowledge is foundational before tackling complex real-world engine modeling and simulations. Benchmark for advanced models. More detailed computational engine models often use idealized cycles like the dual cycle as a starting point or for validation. Brayton cycle. It is used for gas turbines only, where both the compression and expansion processes take place in rotating machinery. Gas turbines usually operate on an open cycle. An open cycle gas turbine engine is drawn into the compressor, where its temperature and pressure are raised. The high-pressure air proceeds into the combustion chamber, where the fuel is burned at constant pressure. The resulting high-temperature gases then enter the turbine, where they expand to the atmospheric pressure while producing power. The exhaust gases leaving the turbine are thrown out, not recirculated, causing the cycle to be classified as an open cycle. Here the compression and expansion processes remain the same, but the combustion process is replaced by a constant pressure heat addition process from an external source, and the exhaust process is replaced by a constant pressure heat rejection process to the ambient air. The ideal cycle that the working fluid undergoes in this closed loop is the Brayton cycle, which is made up of 4 internally reversible processes. 1 to 2 isentropic compression, in a compressor. 2 to 3 constant pressure heat addition. 3 to 4 isentropic expansion, in a turbine. 4 to 1 constant pressure heat rejection. The TS and PV diagram's ideal Brayton cycle. Processes 1 to 2 and 3 to 4 are isentropic, and P2 equals P3 and P4 equals P1. Where is the pressure ratio and K is the specific heat ratio. The air in gas turbines performs 2 important functions. It supplies the necessary oxidant for the complete combustion of the fuel, and it serves as a coolant to keep the temperature of various components within safe limits. Also, the mass flow rate through the turbine is greater than that through the compressor, the difference being equal to the mass flow rate of the fuel. Many modern marine propulsion systems use gas turbines together with diesel engines because of the high fuel consumption of simple cycle gas turbine engines. In combined diesel and gas turbine systems, diesel is used to provide for efficient low power and cruise operation, and gas turbine is used when high speeds are needed. Usually more than 1/2 of the turbine work output is used to drive the compressor. The fraction of the turbine work used to drive the compressor is called the back work ratio. Just enough power to drive the compressor and a small generator to power the auxiliary equipment. In gas turbine power plants, the ratio of the compressor work to the turbine work, called the back work ratio. Increasing the turbine inlets, or firing, temperatures. Increasing the efficiencies of turbomachinery components. Adding modifications to the basic cycle. The network of a gas turbine cycle is the difference between the turbine work output and the compressor work input, and it can be increased by either decreasing the compressor work or increasing the turbine work, or both. The work required to compress a gas between two specified pressures can be decreased by carrying out the compression process in stages and cooling the gas in between, that is, using multistage compression with intercooling. As the number of stages is increased, the compression process becomes nearly isothermal at the compressor inlet temperature, and the compression work decreases. Likewise, the work output of a turbine operating between two pressure levels can be increased by expanding the gas in stages and reheating it in between, that is, utilizing multistage expansion with reheating. This is accomplished without raising the maximum temperature in the cycle 1 AC. As the number of stages is increased, intercooling, the expansion process becomes nearly isothermal. The steady flow of work inputs to a single work is proportional to the specific volume of the fluid, and a two-stage compressor with intercooling, the specific volume of the working fluid should be as low as possible during a compression process and as high as possible during an expansion process. This is precisely what intercooling and reheating accomplish. In the Brayton diagram of a Brayton cycle, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of the air leaving the compressor. Therefore, the high-pressure air leaving the compressor can be heated by transferring heat to it from the hot exhaust gases in a counterflow heat exchanger, which is also known as a regenerator or a recuperator. The Brayton diagram of a Brayton cycle increases as a result of regeneration, since the portion of energy of the exhaust gases that is normally rejected to the surroundings is now used to preheat the air entering the combustion chamber. The actual and maximum heat transfers from the exhaust gases to the air can be expressed as: the extent to which a regenerator approaches an ideal regenerator is called the effectiveness and is defined as: the effectiveness of most regenerators used in practice is below 0.85. Under the cold air standard assumptions, the thermal efficiency of an ideal Brayton cycle with regeneration is. Therefore, the thermal efficiency of an ideal Brayton cycle with regeneration depends on the ratio of the minimum to maximum temperatures as well as the pressure ratio. The network of a gas turbine cycle is the difference between the turbine work output and the compressor work input. The work required to compress a gas between two specified pressures can be decreased by carrying out the compression process in stages and cooling the gas in between, that is, using multistage compression with intercooling. As the number of stages is increased, the compression process becomes nearly isothermal at the compressor inlet temperature, and the compression work decreases. The work output of a turbine operating between two pressure levels can be increased by expanding the gas in stages and reheating it in between, that is, utilizing multistage expansion with reheating. As the number of stages is increased, the expansion process becomes nearly isothermal. The steady flow compression or expansion work is proportional to the specific volume of the fluid. Therefore, the specific volume of the working fluid should be as low as possible during a compression process and as high as possible during an expansion process. The Brayton cycle with intercooling, reheating, and regeneration. The gas enters the first stage of the compressor at state 1, is compressed isentropically to an intermediate pressure P2, is cooled at constant pressure to state 3, T3 equals T1, and is compressed in the second stage isentropically to the final pressure P4. At state 4 the gas enters the regenerator, where it is heated to T5 at constant pressure. In an ideal regenerator, the gas leaves the regenerator at the temperature of the turbine exhaust, that is, T5 equals T9. The primary heat addition, or combustion, process takes place between states 5 and 6. The gas enters the first stage of the turbine at state 6 and expands isentropically to state 7, where it enters the reheater. It is reheated at constant pressure to state 8, T8 equals T6, where it enters the second stage of the turbine. The gas exits the turbine at state 9 and enters the regenerator, where it is cooled to state 10 at constant pressure. The cycle is completed by cooling the gas to the initial state, or purging the exhaust gases. The work input to a two-stage compressor is minimized when equal pressure ratios are maintained across each stage. This procedure also maximizes the turbine work output. For best performance, if the number of compression and expansion stages is increased, the ideal gas turbine cycle with intercooling, reheating, and regeneration approaches the Ericsson cycle. A Stirling and Ericsson cycle borrows energy from the working processes during one part by two constant volume regeneration without interest in the Stirling cycle and by two constant pressure regeneration processes in the Ericsson cycle. Both cycles utilize regeneration, a process during which heat is transferred to a thermal energy storage device, called a regenerator, during one part of the cycle and is transferred back to the working fluid during another part of the cycle. The TS and PV diagrams of the Stirling cycle, which is made up of 4 totally reversible processes. 1 to 2T equals constant expansion, heat addition from the external source. 2 to 3V equals constant regeneration, internal heat transfer from the working fluid to the regenerator. 3 to 4T equals constant compression, heat rejection to the external sink. 4 to 1V equals constant regeneration, internal heat transfer from the regenerator back to the working fluid. The execution of the Stirling cycle. The Ericsson cycle is very much like the Stirling cycle, except that the two constant volume processes are replaced by two constant pressure processes. Both the Stirling and Ericsson cycles are totally reversible, as is the Carnot cycle, and thus according to the Carnot principle, all three cycles must have the same thermal efficiency when operating between the same temperature limits. Stirling engines can power pumps to move fluids like water, air, and gases. Stirling engines have many applications, including submarines. Stirling engines allow submarines to stay submerged for longer periods of time without surfacing to recharge batteries. Solar power plants. Stirling engines are the only piston engines that can efficiently convert solar energy into mechanical and then electrical energy. Waste heat recovery. Stirling engines can recover waste heat, especially in heavy industries. Cooling and heating. Stirling engines can be used for both cooling and heating processes. Refrigeration. Stirling engines can be used for refrigeration, such as in miniature cryogenic refrigerators for missile guidance and night vision equipment. Irrigation pumps. Stirling engines can be used as irrigation pumps. Low-capacity generators. Stirling engines can be used as low-capacity generators for long-term unattended operation in remote locations. Marine propulsion. Stirling engines can be used for marine propulsion. Yacht or recreational vehicle power generation. Stirling engines can be used for yacht or recreational vehicle power generation. Ericsson engines have many potential applications are well suited for converting low-power solar energy. Submarines. Ericsson engines could be used to power submarines. Expeditionary power. Ericsson engines could be used for expeditionary power. Refrigeration. Ericsson engines could be used for refrigeration. Micro-CHP. Ericsson engines could be used for micro-CHP, combined heat and power, from conventional fossil fuels or from biomass. Waste heat recovery. Ericsson engines could be used for waste heat recovery. Isentropic process involves no irreversibility since the effect of the ideal process is always to downgrade the performance of engineering devices. Thus, the ideal process that can serve as a suitable model for adiabatic steady flow devices is the isentropic process. The entropy of a fixed mass can be changed by 1. Heat transfer and 2. Irreversibilities. The entropy of a fixed mass does not change during a process that is internally reversible and adiabatic. A process during which the entropy remains constant is called an isentropic process. It is characterized by the isentropic process involves no irreversibilities and serves as the ideal process for adiabatic devices. A parameter that expresses quantitatively how efficiently an actual device approximates an idealized one. This parameter is the isentropic or adiabatic efficiency, which is a measure of the deviation of actual processes from the corresponding idealized ones. The desired output of a turbine is the work produced, and the isentropic efficiency of a turbine is defined as the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic. Usually the changes in kinetic and potential energies associated with an adiabatic stream flowing through a turbine are small relative to the change in enthalpy and can be neglected. Then the work output of an adiabatic turbine simply becomes the change in enthalpy, where H2A and H2S are the enthalpy values at the exit state for actual and isentropic processes, respectively. The desired output of a turbine is the work produced, and the isentropic efficiency of a turbine is defined as the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic. Usually the changes in kinetic and potential energies associated with a fluid stream flowing through a turbine are small relative to the change in enthalpy and can be neglected. Then the work output of an adiabatic turbine simply becomes the change in enthalpy, where H2A and H2S are the enthalpy values at the exit state for actual and isentropic processes, respectively. The value of NT greatly depends on the design of the individual components that make up the turbine. Well-designed, large turbines have isentropic efficiencies above 90%. For small turbines, however, it may drop even below 70%. The value of the isentropic efficiency of a turbine is determined by measuring the actual work output of the turbine and by calculating the isentropic work output for the measured inlet conditions and the exit pressure. The HS diagram for the actual and isentropic processes of an adiabatic turbine. The isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input. The isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input. When the changes in kinetic and potential energies of the gas being compressed are negligible, the work input to an adiabatic compressor becomes equal to the change in enthalpy. Notice that the isentropic of compressor efficiency is defined with the isentropic work input in the numerator instead of in the denominator. This is because Ws is a smaller quantity than Wa, and this definition prevents Nc from becoming greater than 100%. When the changes in kinetic and potential energies of the gas being compressed are negligible, the work input to an adiabatic compressor becomes equal to the change in enthalpy, where H2A and H2S are the enthalpy values at the exit state for actual and isentropic compression processes, respectively. Again, the value of Nc greatly depends on the design of the compressor. Well-designed compressors have isentropic efficiencies that range from 80 to 90%. When the changes in potential and kinetic energies of a liquid are negligible, the isentropic efficiency of a pump is defined similarly as the HS diagram of the actual and isentropic processes of an adiabatic compressor. Nozzles are essentially adiabatic devices and are used to accelerate a fluid. Therefore, the isentropic process serves as a suitable model for nozzles. The isentropic efficiency of a nozzle is defined as the ratio of the actual kinetic energy of the fluid at the nozzle exit to the kinetic energy value at the exit of an isentropic nozzle for the same inlet state and exit pressure. That is, the exit pressure is the same for both the actual and isentropic processes, but the exit state is different. Nozzles involve no work interactions, and the fluid experiences little or no change in its potential energy as it flows through the device. If, in addition, the inlet velocity of the fluid is small relative to the exit velocity, the energy balance for this steady flow device reduces to. Then the isentropic efficiency of the nozzle can be expressed in terms of enthalpies as, where H2A and H2S are the enthalpy values at the nozzle exit for the actual and isentropic processes, respectively. Isentropic efficiencies of nozzles are typically above 90%, and nozzle efficiencies above 95% are not uncommon. The HS diagram of the actual and isentropic processes of an adiabatic nozzle. In steam or gas power plants, the pressure rise in the pump or compressor is equal to the pressure drop in the turbine if we disregard the pressure losses in various other components. In steam power plants, the pump handles liquid, which has a very small specific volume, and the turbine handles vapor, whose specific volume is many times larger. Therefore, the work output of the turbine is much larger than the work input to the pump. This is one of the reasons for the widespread use of steam power plants in electric power generation. In gas power plants, the working fluid, typically air, is compressed in the gas phase, and a considerable portion of the work output of the turbine is consumed by the compressor. As a result, a gas power plant delivers less net work per unit mass of the working fluid. The Humphrey cycle is a thermodynamic cycle similar to the pulse detonation engine and pulse compression detonation system cycles. It may be considered to be a modification of the Brayton cycle, in which the constant pressure heat addition process of the Brayton cycle is replaced by a constant volume heat addition process. Hence, the ideal Humphrey cycle consists of 4 processes: reversible, adiabatic, isentropic, compression of the incoming gas. During this step, incoming gas is compressed, usually by turbomachinery. Stagnation pressure and temperature increase because of the work done on the gas by the compressor. Entropy is unchanged. Static pressure and density of the gas increase. Constant volume heat addition. In this step, heat is added while the gas is kept at constant volume. In most cases, Humphrey cycle engines are considered open cycles, meaning that air flows through continuously, which makes it difficult to have a constant volume during the addition of heat. Hence, instead of a deflagrative flame, which is commonly used in Brayton cycles, constant pressure heat addition, the combustion mode is detonative. Deflagration is a subsonic combustion process where the flame front propagates through the fuel-air mixture at speeds less than the speed of sound. It's a relatively slow and controlled burning process, producing a rapid release of heat but without explosive shock waves. In being detonative, the heat addition happens only for a small sector volume of premixture, in a combustor annulus, at a constant volume, while the remaining sections refill the chamber with fresh incoming premixture. This method allows for continuous flow in the system while at the same time achieving the pseudo-constant volume requirement for the heat addition process. Reversible, adiabatic, isentropic, expansion of the gas. During this step, incoming gas is expanded, usually by turbomachinery. Stagnation pressure and temperature decrease because of the work extracted from the gas by the turbine. Entropy is unchanged. Static pressure and density of the gas decrease. Constant pressure heat rejection. In this step, heat is removed from the working fluid while the fluid remains at constant pressure. In open cycle engines, this process usually represents expulsion of the gas from the engine, where it quickly equalizes to ambient pressure and slowly loses heat to the atmosphere, which is considered to be an infinitely large reservoir for heat storage, with constant pressure and temperature. Gas turbines. The Humphrey cycle is indeed a thermodynamic cycle related to gas turbines, but it's not the most commonly used cycle in aviation gas turbines. Theoretical cycle with constant volume heat addition, potentially more efficient, but less practical. The Humphrey cycle can be used to improve the overall thermal efficiency of small-scale power generation systems.